Hello everyone, welcome to my YouTube channel on engineering mathematics.
In this video, I am going to discuss how to evaluate double integrals in Cartesian coordinates by changing them to polar coordinates. The method consists of only 4 steps. In step 1, we draw the curves which bounds the region of integration and recognize the region of integration out of it. For this, we will take help of limits of the double integration. In step 2, we substitute x is equal to r cos theta and y is equal to r sin theta, which is relation between Cartesian and polar coordinates, and we transform the equations of the boundary curves from Cartesian x, y coordinates to polar r, theta coordinates. In step 3, we find the limits for r and theta. And finally, in step 4, we use the substitution same as step 2 and change the integrand in r, theta. We also replace dx dy to r dr d theta and evaluate the integral. To transform dx dy to r dr d theta, we need a Jacobian factor which is r here, which comes from the relation x is equal to r cos theta and y is equal to r sin theta. I will not go deep into this transformation from dx dy to r dr d theta. You just remember this dx dy is transformed to r dr d theta by using the relation x is equal to r cos theta and y is equal to r sin theta. Now let's take a look of the examples. In this first example, we are asked to evaluate the integral given by double integration of x square plus y square dx dy, where x limits are 0 and under root 9 minus y square and y limits are 0 and 3. Now let's go for the solution. In step 1, we recognize the equation of the curves which bounds the region of integration and then we draw them. Here the region of integration is bounded by the curves x is equal to 0, x is equal to under root 9 minus y square, that is x square plus y square is equal to 9, that is 3 square, and y is equal to 0 and y is equal to 3. Let's draw these curves on Cartesian xy plane. This is your x is equal to 0, that is y axis. This circle is nothing but x square plus y square is equal to 9, which is centered at origin and radius 3. Y is equal to 0 is x axis and y is equal to 3 is this straight line passing through point y is equal to 3 and parallel to x axis. Now let's go for step 2. In step 2, we are going to substitute x is equal to r cos theta and y is equal to r sin theta in the equation of curves which bounds the region of integration. This first equation, x is equal to under root 9 minus y square, that is x square plus y square is equal to 9, gives us r square is equal to 9. See, x is r cos theta, y is r sin theta. So you will have x square plus y square, that is r square into cos square theta plus sin square theta is equal to 9. But cos square theta plus sin square theta is 1. So we left with r square is equal to 9, that is r is equal to 3. From the second equation, that is x is equal to 0, we get r cos theta is equal to 0. That is either r is equal to 0 or cos theta is equal to 0. Cos theta is 0 at theta is equal to pi by 2. Therefore, we get either r is equal to 0 or theta is equal to pi by 2. Now, let's take the equation y is equal to 0. From y is equal to 0, we get r sin theta is equal to 0. Therefore, either r is equal to 0 or sin theta is equal to 0. And we know that sin theta is 0 at theta is equal to 0. From this, we see r varies from 0 to 3 and theta varies from 0 to pi by 2. Note that there is one more equation y is equal to 3 which we are not using for finding any limits of r or theta, because y is equal to 3 contributes only a single point in this region of integration and this point is also covered by other two curves x is equal to 0 and x square plus y square is equal to 9. So we are neglecting this y is equal to 3 for finding limits for r and theta. Now let's finally transform this double integral from Cartesian coordinates to polar coordinates. First we transform this integrand. This x square, after substituting x is equal to r cos theta, becomes r cos theta whole square, and y square becomes r sin theta whole square. We have seen dx dy after transformation becomes r dr d theta. Now let's talk about the limits. We have seen r varies from 0 to 3 and theta varies from 0 to pi by 2. Note that these limits can also be found out by observing the region of integration. Here you can clearly see that modulus r varies from 0 to 3 over this circle, and theta varies from this positive x-axis to positive y-axis, that is from 0 to pi by 2. By practicing more such examples, you will be able to find out these limits of r and theta by observation, that is by observing the region of integration. Now let us proceed to evaluate this integral. I'll take out this r square, which is common in these two terms. We get inside cos square theta plus sin square theta and r dr d theta as it is. But cos square theta plus sin square theta is 1, so we left with r square into r, that is r cube dr d theta. Now let us first integrate this r cube with respect to r. Its integration is r raised to 4 upon 4 over the limit 0 to 3. After substituting these limits, we get 3 raised to 4 upon 4 minus 0. This 3 raised to 4 upon 4 is constant. We can take it out. Finally, integrand becomes 1 into d theta. Its integration is just theta over the limit 0 to pi by 2. After substituting these limits in theta, we get value of this double integral is 3 raised to 4 upon 4 into pi by 2. I hope guys you understood this example. Now let us go ahead for example number 2. Here we have to first transform this double integral in x and y into polar coordinates, and then we have to evaluate it. The integration is double integration of x dx dy over the limits y to 2 and 0 to 2. Let's go for step-by-step solution. In step 1, we recognize the equation of the curves which bounds the region of integration, and then we draw them. Here the region of integration is bounded by the curves x is equal to y, x is equal to 2, y is equal to 0 and y is equal to 2. Let's draw them. X is equal to y is a line passing through origin making an angle of 45 degree with the positive x-axis. If you do not know about these equations, you can simply find out the points on these curves and plot them and finally join those points to draw that curve. X is equal to 2 is a straight line passing through point x is equal to 2 and parallel to y-axis. Y is equal to 0 is x-axis, and y is equal to 2 is the straight line passing through point y is equal to 2 parallel to x-axis. Finally, this region of integration is shown by this orange shaded part. Now let's transform this system or double integration into polar coordinates by substituting x is equal to r cos theta and y is equal to r sin theta. Let us first bother about the limits. For that, we will put these substitutions in the equation of curves which bounds the region of integration. First equation is x is equal to y. From this, we get r cos theta is equal to r sin theta. These r's will get cancelled. We take this cos theta on the other side to get tan theta is equal to 1. And we know that tan theta is 1 at theta is equal to pi by 4. Now let's go for another equation. X is equal to 2. X is equal to 2 gives us r cos theta is equal to 2. Therefore, r is equal to 2 upon cos theta. Now let us take another equation, y is equal to 0. From y is equal to 0, we get r sin theta is equal to 0. That is either r is equal to 0 or sin theta is equal to 0. But sin theta is 0 at theta is equal to 0. Finally, we get all the limits for r and theta. So we see r varies from 0 to 2 by cos theta and theta varies from 0 to pi by 4. You can clearly observe this from this region of integration. Theta is varying from positive x-axis to this line y is equal to x. On positive x-axis theta is 0 and on the line y is equal to x, theta is pi by 4. So clearly theta is varying from 0 to pi by 4 and modulus r is varying from 0 to any point on this y is equal to x as well as y is equal to 2. So r is varying from 0 to 2 by cos theta. You may wonder, I haven't taken the equation y is equal to 2 for calculating any of the limit. Because y is equal to 2 contributes only a single point on the boundary of the region of integration. And this point is also covered in the other two equations, x is equal to 2 as well as y is equal to x. So we neglect this point for calculating limits for r and theta. Now let us proceed for transformation of this double integration from Cartesian to polar coordinates. First we transform the integrand. For that we substitute x is equal to r cos theta and dx dy is equal to r dr d theta. So integrand becomes r cos theta and dx dy becomes r dr d theta. We have already calculated limits for r and theta. We'll simply write them over here. R varies from 0 to 2 by cos theta and theta varies from 0 to pi by 4. I hope guys you understood this transformation. Now let us proceed for evaluation part. First we integrate the inside integral with respect to r. Integrand is r square into cos theta. Since we are integrating with respect to r, we will keep cos theta term constant. Integration of r square is r cube by 3 over the limit 0 to 2 by cos theta. After substituting the upper limit in r, we get 2 cube upon cos cube theta. This 1 by 3 is taken out. After substituting 0 in r, we get 0. And this cos theta d theta as it is. When we multiply this cos theta d theta inside, this 1 cos theta from the denominator and this cos theta will get cancelled. 2 cube is constant, you can take it out. Finally, 1 by cos square theta, we write as sec square theta d theta. And integration of sec square theta is tan theta. Limits are 0 to pi by 4. Let us substitute these limits in theta. First, the upper limit. Tan of pi by 4 is 1 and then lower limit after substitution we get tan of 0 that is 0. So the final answer or value of the double integral is 2 cube by 3. I hope guys you understood this solution. Now let us proceed for example number 3. Here we have to change the Cartesian coordinate system of this double integral into polar coordinates and we have to evaluate it. The given integral is double integration of dx dy. So integrand is 1. And limits are y square by 4a to y and 0 to 4a. Let us go with step-by-step solution. In step 1, we recognize the equation of curves which bounds the region of integration and then we draw them. Here the region of integration is bounded by x is equal to y square by 4a, x is equal to y is equal to 0 and y is equal to 4a. Let's draw these curves on Cartesian plane. X is equal to y is this straight line passing through origin making an angle of 45 degree with positive x-axis. X is equal to y square by 4a is a parabola along y-axis opening to the right. Y is equal to 0 is x-axis. And y is equal to 4a is this line passing through point y is equal to 4a which is parallel to x-axis. Here, the region of integration is shown by this pink shaded part. Now let us transform this double integral from Cartesian to polar coordinates by substituting x is equal to r cos theta and y is equal to r sin theta. First we find the limits for r and theta. For that, we take equations of curves which bounds the region of integration. Consider this equation x is equal to y square by 4a. After substituting r cos theta and r sin theta for x and y respectively, we get r cos theta is equal to r square sin square theta upon 4a. This r and square will get cancelled. We get cos theta is equal to r sin square theta upon 4a. Therefore, r is equal to 4a cos theta upon sin square theta. This is just a little bit rearrangement of the terms. Now, from second equation, x is equal to y, we get r cos theta is equal to r sin theta. This r and this r will get cancelled. Taking this cos theta on the other side, we get tan theta is equal to 1. And we know tan theta is 1 at theta is equal to pi by 4. Note that here theta varies from this x is equal to y line to positive y axis, because this curve parabola touches positive y axis, so theta varies from line x is equal to y to line y axis. Y axis is nothing but x is equal to 0. Therefore, we get r cos theta is equal to 0. That is either r is equal to 0 or cos theta is equal to 0. And we know that cos theta is 0 at theta is equal to pi by 2. So here r varies from 0 to 4a cos theta upon sin square theta, and theta varies from pi by 4 to pi by 2. Now let us transform this double integral from Cartesian coordinates to polar coordinates. First we transform the integrand. Integrand is just 1. So this dx dy now becomes r dr d theta. Now write down the limits that we have calculated on previous slide. R varies from 0 to 4a cos theta upon sin square theta, and theta varies from pi by 4 to pi by 2. Now let us evaluate this integral. Integration of r is r square upon 2 over the limits 0 to 4a cos theta upon sin square theta. This 1 by 2 is constant, we can take it out. After substituting these limits in r square, we get 4 square a square into cos square theta upon sin raised to 4 theta. When we substitute lower limit in r, we get 0. This 4 square a square is constant, we can take it out. It becomes 16a square, and this 1 by 2 as it is. This cos square theta upon sin raised to 4 theta can be written as cot square theta into cosec square theta. For this, you split this sin raised to 4 theta as sin square theta into sin square theta. Then cos square theta upon sin square theta becomes cot square theta, and 1 upon sin square theta becomes cosec square theta. Now let's evaluate this integral. We put cot theta is equal to t. Therefore, its differentiation minus cosec square theta d theta is equal to dt. Therefore, this integral now becomes minus 8a square integral from pi by 4 to pi by 2 of t square into dt. Integration of t square is t cube by 3. After substituting t is equal to cot theta, we get cot cube theta over here, and limits are pi by 4 to pi by 2. Now let us substitute these limits in theta. We get cot cube pi by 2 minus cot cube pi by 4. Cot cube pi by 2 is 0 and cot cube pi by 4 is 1. Therefore, final solution or value of this double integral is plus 8a square by 3. I hope guys you understood this solution. Now let us proceed for next example. Here we are asked to evaluate the integral by changing to polar coordinates, and the integral is double integration of x upon under root x square plus y square dx dy over the limits 0 to under root 2a x minus x square and 0 to 2a. Let us go for the step-by-step solution. In step 1, we recognize the equation of the curves which bounds the region of integration, and then we draw them. Here the region of integration is bounded by y is equal to 0, y is equal to under root 2ax minus x square, that is x square plus y square is equal to 2ax, and x is equal to 0 and x is equal to 2a. Here note that x square plus y square is equal to 2ax is a circle with center a comma 0 and radius a. You can compare this equation of a circle with standard equation of a circle given by x square plus y square plus 2gx plus 2fy plus c is equal to 0, in which center is given by the coordinates minus g comma minus f and radius is given by the formula under root g square plus f square minus c. When we draw this circle, we get this figure. This circle is centered at say a comma 0. I am considering here a is equal to 1 just for the sake of drawing this picture. Then x is equal to 2a will be this straight line passing through x is equal to 2 or x is equal to a, you can say, which is parallel to y axis. Y is equal to 0 is x axis and x is equal to 0 is y axis. Now let us transform this double integral into polar coordinates by substituting x is equal to r cos theta and y is equal to r sin theta. First we transform these limits. For that, consider the equation of upper limit, that is this circle x square plus y square is equal to 2ax. After substituting these relations in x and y, we get r square is equal to 2a r cos theta. One r on left hand side will get cancelled with this r, so we get r is equal to 2a cos theta. From equation y is equal to 0, we get r sin theta is equal to 0, that is r is equal to 0 or theta is equal to 0. Also note that theta varies from positive x axis to positive y axis. Therefore, theta actually varies from 0 to pi by 2. So limits for r are 0 to 2a cos theta and theta are 0 to pi by 2. Now let's transform this double integral into polar coordinates. First we transform the integrand. Here we substitute x is equal to r cos theta and y is equal to r sin theta. We also replace dx dy by r dr d theta. So in the numerator we get r cos theta. Denominator x square plus y square becomes under root of r square, that is r, and dx dy is r dr d theta. Limits for r were 0 to 2a cos theta and theta were 0 to pi by 2. Now this r and this r will get cancelled. So in integrand we get only r cos theta. Let us integrate this with respect to dr. For that we keep cos theta constant. Integration of r is r square by 2 over these limits 0 to 2a cos theta. Substituting these limits in r and taking out this 1 by 2, we get 2a the whole square, that is 4a square into cos square theta minus 0. After substituting lower limit, we get 0. This 4a square is constant, we can take it out. So outside we have 4a square upon 2, that is 2a square, into integral from 0 to pi by 2 of cos square theta into cos theta d theta. This cos square theta can be written as 1 minus sin square theta using the identity cos square theta plus sin square theta is equal to 1. Now finally, to evaluate this integral, we are going to substitute sin theta is equal to t, differentiating which we get cos theta d theta is equal to dt. Therefore, this integral now becomes 4a square upon 2 into integral from 0 to pi by 2 of 1 minus t square into cos theta d theta is dt. Integration of 1 with respect to dt is t and t square integration is t cube by 3 over the limit 0 to pi by 2. Remember, these limits are of not t, they are of theta. So we transform t again into theta by using this relation. So here we get sin theta minus sin cube theta upon 3. After substituting the upper limit, we get sin pi by 2, which is 1, minus sin cube pi by 2, which is again 1 upon 3, minus substituting lower limit 0 in theta, we get sin 0, that is 0, and sin cube theta 0, which is 0 again. So final solution is 4a square upon 2 into 1 minus 1 by 3, that is 4a square upon 3. I hope guys you understood these examples. Now it is your turn to solve some examples. Next, I'm going to show you a couple of examples that you have to solve on your own, and write me in comment box whether you are able to solve these examples or not. Here is the fifth example. Consider this as a practice example. Its transformation I am giving you over here so that you can tally your answer. Similarly, here is example number 6 for you. This is the region of integration and its polar form is given over here. Guys, please write me in comment box whether you like this video or not. If you like this video, please click the like button and share this among your friends. I'll be coming with more such interesting topics in my upcoming videos. Till then, keep watching. Thank you all of you.
Thank you for watching this video. Please subscribe my YouTube channel and press the bell icon to get updates about my new videos.